So just to give you a bit of an introduction about myself, so my name is Craig. I joined the CMM in 2022 and my background is chemistry. So firstly I did a PhD at the University of Nottingham in nanomaterials chemistry, and before that I did a master's degree with a year spent on exchange at the University of Queensland. My areas of expertise are XPS, X-ray Photoelectron Spectroscopy, and also TEM, transmission electron microscopy, and just in general any forms of elemental analysis, characterization and nanomaterial synthesis. For XPS, it gives the rapid evaluation of elemental composition of solids. In terms of sensitivity, weight percentage we get down to parts per thousand. It depends on the elements. It's sensitive to all elements apart from hydrogen and helium, which puts it at quite a big advantage compared to other X-ray techniques such as XRF. It's fairly quantitative, plus or minus 10% relative. What's quite nice about it from a chemistry point of view is that it contains information on chemical speciation. The binding energies and the shapes that we get shift depending on the oxidation state of the elements that we're looking at. It's a non-destructive technique, unlike quite a lot of other techniques that you might use such as TEM or SEM, and quite crucially it's a surface sensitive technique. The information that we get comes exclusively from the top 5 to 10 nanometers of a sample, and so we need to bear this in mind when we do any sort of analysis. For XPS, the sample needs to be a solid or a powder or a thin film. This is because it is a technique that's performed under ultra high vacuum, and so liquids or gases, we can't put these into the chamber. As a complementary technique, something like electron microscopy or optical microscopy could help you out. In terms of the concentration limits, like I say, we're down to about parts per thousand, 0.1%. If you need something better than that, we can look at SIMS, or we can look at doing XRF or IR spectroscopy. In terms of resolution, we aren't able to look at microscopic features, anything sort of below 10 microns. This is because we just can't really focus X-rays in the way that we can focus electrons when we do electron microscopy. So if you are looking at some really fine resolution, nanoscale or microscale analysis, we do need to consider SEM, TEM or EDX or wheels. And finally, the physical properties of samples. The good news is we can look at a wide range of different materials, conducting samples, non-conducting samples, insulating samples. We just need to be aware of that when we prepare the samples. So it's similar to, doing optical microscopy or doing an SEM with a coating. With XPS we can't coat the samples because it is a surface technique. So that's where XPS does shine through over something like SEM. We use X-rays to excite electrons from the surface atoms of a sample. So we're talking the top 10 nanometers. All elements have electrons, and so essentially all elements can be detected other than hydrogen and helium. Since all elements have a unique shell structure, which is unique to the sample, we can discriminate between which elements are present based on the binding energy and based on the shapes of the peaks. The peak intensity is related to the atomic percentage once we take into account a few considerations regarding how sensitive elements are to XPS. And smaller peak shifts can identify local environment of the atoms as well. So when we talk about XPS and X-rays, X-rays cover quite a wide spectrum. We can have soft X-rays, we can have hard X-rays. For XPS, we use soft X-rays. Typically these are low energy X-rays. We're talking about 100 electron volts to 3000 electron volts. And how does that compare to medical X-rays? When we hear the word X-ray, we think automatically of broken bones. When you go to the hospital but have a medical X-ray, these are what we call hard X-rays. These are a lot higher in energy, and that's because the X-ray needs to penetrate the skin. With XPS, the X-rays sit on the surface of the sample that we're looking at. They just ionize the surface. So these are different X-rays, they're a lot lower in energy. And compared to, for example, to airport X-rays, these are even higher in energy because the X-rays need to penetrate, metals and cases and that sort of thing. So this just gives you the idea of where it sits. So any electron that's been emitted out to an atom by some sort of electromagnetic radiation is a photoelectron. X-rays, in particular low energy X-rays, just happen to have a high probability of exciting photoelectrons, and that's why we use them. Photoelectrons were first observed by Heinrich Hertz. So what he did was he shone UV light onto metal electrodes at high voltage, and he saw that extra sparks were emitted when he switched on this voltage. He wasn't really sure what was happening, he just thought it was cool. 10 years after that, J.J. Thomson discovered electrons. The initial concept was that these were sort of small bodies carrying charge, but it wasn't until Albert Einstein came along 30 years later, he was able to basically say that the energy of the electrons that comes off is related to the light. And then he came up with this equation, that's what he won the Nobel Prize for. Now we'll talk about elemental composition, just so you're familiar with how this relates to XPS and how we can actually use XPS. Firstly, we'll consider electronic structure. So here we've got an atom of carbon. It's got a nucleus which contains 6 protons and 6 neutrons, and it's got these electrons in the outer shell. Atoms comprise of protons, neutrons and electrons. For the purpose of XPS, we only need to consider the electrons. For something like carbon, this is quite simple, but then if we consider something larger, like gold, this has many more electrons. We can start to see how these electrons fill. These electrons sit in a way dictated by what we call the alpha bar principle. So this is just German for building up, and it dictates how we build electrons from right in the middle of the atom to the outer shells. Firstly, we would fill the 1s orbital, then the 2s, then the 2p, then the 3s, 3p, but then we wouldn't go on to the 3d, we'd go on to the 4s. Just, it depends on how the energy levels relate, but we can go through the system for all of the elements. It's good to have an appreciation of the periodic table and the electron configuration of all the atoms. We can describe all of the atoms based on their outer orbitals. Carbon is quite simple. We'd start off with the 1s, then we'd go to the 2s and the 2p. So we need to consider the principal quantum number n. That just describes the shell level, you know, the number. We've also got the orbital angular momentum quantum number L, which describes the type of orbital, whether it's an s, p or a d or an f orbital. And we can start filling the electrons in like so. For carbon, for example, there are 6 electrons, and this is how they fill in. And as we go across the periodic table, we're always adding a proton and an electron one by one. And so as we go across, we begin to fill the shells like so, until eventually on this period, once we get down to neon, we have a full shell. If we consider the electron structure as a whole, we can look at these energy level diagrams. We have n, the principal quantum number, which describes the shell. Then I have L, which describes the type of orbital. And then we actually get splitting. So the energy levels are characterized by the quantum numbers. Spin-orbit coupling splits the levels, and the energies that we get are referred to the vacuum level here. So 1s at the bottom, then we've got the 2s and the 2p, and then the 3s above that. You can also see on the left, I've labelled these as K, L, M. So this is just another type of nomenclature for identifying the orbitals that we have. These were first devised quite a while ago by a guy called Charles Barkla. He named the 1s orbital the K, and he named the 2s the Ls. And this is because he wasn't sure that there might actually be orbitals that were below this that he couldn't see. So he didn't want to label the 1s as A. He thought it'd start off at K, and then at least if any of the others were discovered later on, we could go back. But as it turned out, he was correct. There were no other orbitals below this. So we call this the K shell, then we go to the L shell and the M shell. And as we increase the energy away from the nucleus, this letter increases. We can consider how X-rays interact with matter. Firstly, we consider elastic scattering. So that's the process of taking an X-ray, firing it at an atom, and then X-rays of the same energy coming off. So they're elastically scattered, no energy has been lost along the way. This is the basis for electron diffraction or XRD experiments. Secondly, we can consider inelastic or Compton scattering. So this is when the energy of the X-rays that come off have lost energy. This isn't applicable to XPS, but other techniques it can be relevant to. The thing that is applicable to XPS is the photoelectric effect. So this is where we shine X-rays at a sample, at an atom, and this atom gets ionised and then an electron comes off, and we detect the energy of the electron that's removed. So this is applicable to XPS, but also XRF, X-ray fluorescence. When we think of Einstein, we think of E equals mc squared, but that's not what he actually won the Nobel Prize for. It's for the photoelectric effect and the discovery of that. So we have an X-ray, we shine this at an atom, and an electron gets removed. If we consider this in a mathematical sense, we have an atom A, we have an energy of X-ray h mu. That gives us an ionised atom plus an electron. X-rays in, electrons out. When the photon energy, that's the energy of the X-ray, when that exceeds the binding energy of the electron, the ejected electron will have a kinetic energy given by this. The value of the kinetic energy is equal to the energy of the X-ray that goes in, minus the binding energy, EB, minus the work function. So the work function is a very small, negligible amount. It just depends on the spectrometer that we use, so we can ignore it in this context. So we can rearrange that, so we can see that the X-ray energy, h mu, is equal to the kinetic energy of the electron plus the binding energy of the electron plus the work function. So sometimes it's just easier to see that pictorially. We've got this blue amount here, which is the electron energy that goes in, and completely that would equal the work function, the very small amount, and the binding energy and the kinetic energy. If the electrons are very tightly bound, the binding energy will be higher because we will require much more energy to remove the electrons, and therefore the kinetic energy that we get off will be lower. Conversely, if the electrons are further away from the nucleus, the binding energy will be lower, and therefore their associated kinetic energy would be much higher. With XPS, we measure the kinetic energy, but we report the binding energy. The kinetic energy of the electrons is detected in the instrument, and the binding energy is what is unknown. But using the relationship that we know the energy that we put in, we know the work function of the instrument, and we know the kinetic energy because we've just measured it, we can then work out the binding energy of the electrons. This is what an XPS spectra looks like. We've got the binding energy along the bottom, and then we've got counts along the top. If we consider zinc in this example, if we go back to what we said at the start and we have the diagram showing the energy levels, we can then begin to start seeing why particular peaks appear where they do. So firstly, if we consider the 3s and the 3p orbitals, so these are quite high up on the scale. These are quite loosely bound. Therefore, these have quite a high kinetic energy when they come off because they're not held to the nucleus that heavy. If we then consider the 2p, these have quite a high binding energy, and this is because these are in the L shell. These are tightly bound to the nucleus. And if we look at this diagram, we see that we've got the 1s, and we can't actually see the 1s on this spectrum. And why is that? That's just because the binding energy of the 1s is far too high to remove the electrons. The 1s electrons are very tightly bound to the nucleus, and therefore the energy of the X-rays that we use is not strong enough to remove them. If we wanted to access the 1s electrons in this way, we would have to use a higher energy source. Also the 3D, these are very loosely bound. We don't actually see them on there. They would be very lower on the binding energy scale. They're very easy to remove. We can see they've got a very small binding energy that have a very large kinetic energy. Other things to consider, for the 2p and the 3p, we actually get splitting of the orbitals. So we've got 2 peaks for the 2p and the 3p, but for the 1s, we've only got 1 peak. And the splitting is due to spin-orbit coupling between the angular momentum vector of the orbital and the electron spin. So the coupling is either parallel or anti-parallel. When there's a parallel alignment, this is less favourable and is therefore at a higher energy, and so it appears at slightly lower binding energy. We can go through all of the orbitals. We don't get any splitting for the s orbital, but for the p, the d and the f, we get a splitting. And these always appear at a particular ratio. For example, the p orbitals always split at a ratio of 2 to 1. The d orbitals always split at a ratio of 3 to 2, and the f orbitals always split at a ratio of 4 to 3. The ratio that the orbitals split is always fixed. However, the separation between them depends on the atom. This is atom specific, but the ratio is always constant. So we see that there's a little bit of a strange background. When we're at the high binding energy section, the background is raised, whereas at the lower end, it's much lower. And this is just due to different electrons that come off. When we get a main photoelectron peak, these are caused by elastic electrons, so electrons that haven't lost any energy between leaving the sample and reaching the detector. However, you'll see that there are also inelastic electrons, and basically this is because some of the electrons sadly don't reach the detector, they get lost along the way, and so these just end up in the background. So whenever we fit any curves, we need to bear in mind that the background might be a different shape, and that's due to inelastic electrons that we've lost along the way. We've also got these other features here which we haven't analysed. So we need to really see where these are from. These aren't caused by photoelectron peaks. But to look into these in more detail, we need to consider the processes again. Firstly, the primary process that we have is photoionization. So we shine X-rays at a sample, we lose an electron, we've got the atom A, we've got the energy of the X-ray that goes in, and then we get the ionized atom and we get an electron that comes off. Some other thing that can happen is electron ionization, so we can have an atom and then an electron that we've lost previously from another atom can knock out a second electron and will basically analyze the sample. So electron comes in, knocks out another electron. This tends not to happen. What we do need to consider though is the relaxation processes. So there are 2 types of relaxation processes. So X-ray goes in, electron comes off, and then when the electron goes off, a hold is left by this photoelectron. This isn't a stable arrangement, and so an electron from a higher shell will fall down to occupy the lower shell just to have a much stable configuration. But then in order to conserve momentum, something needs to happen. When the electron falls down, the photon leaves, and we get a fluorescence, and that's the basis of XRF, X-ray fluorescence, which is a technique. One thing that also happens is instead of a photon being emitted in the form of a fluorescence, we can also get an Auger electron that leaves. So we get what's called an Auger emission. And these are the peaks that we see in the spectrum. Basically, most elements will either give off a fluorescence or an Auger. As the atomic number increases, the likelihood of the fluorescence increases and the likelihood of the Auger decreases. Auger electrons are quite common for the lower elements, but we do also see them along the way. Augers are very challenging to analyse and fit. They have quite broad shapes, quite broad ranges. They may overlap with peaks of interest. What's quite interesting though is that their kinetic energy is always fixed. For Auger emission, what we need to think is that all the analyzer of the XPS does is count electrons and detect their kinetic energy. It doesn't really know where these electrons are from. It doesn't know if these are binding energy electrons, photoelectrons, or Auger electrons. So with XPS, we measure the kinetic energy of electrons, but we report their binding energy. Auger electrons don't have an associated binding energy because they aren't photoelectrons, so they're not bound to anything. They have a fixed kinetic energy. And so we always report Auger electrons as a kinetic energy. We can change the scale. Therefore, changing the X-ray input energy will appear to shift their binding energy. And so we can move the peaks around if there's an overlap with anything else. For example, they have a fixed kinetic energy. However, we can put in a higher X-ray energy, and then this will appear that the binding energy has changed, but it hasn't. It's just the kinetic energy stayed the same. So if ever we get an overlap between photoelectron peaks and Auger peaks, we can change the binding energy of the X-rays, and this will shift the position for us. We have a sample. We shine X-rays at the sample. This gives off photoelectrons. These electrons then pass through a series of different optics, through a hemispherical analyzer, and hit a detector. And that's the basic principle of all XPS instruments. This is the old instrument that we have. This is called an Axis Ultra delay line detector instrument. This is about 20 years old now, and we have an X-ray source. The X-ray's got monochromator, they hit the sample, electrons are produced, they pass through an analyzer, and we get detected. Nowadays, this is the one that we use in the lab at UQ. This is the Axis Super Plus, so this is the top of the range one. It looks different to the older one, but it's the same principle. It just, the technology's increased and it's, it's covered up. We don't see most of the features here. So X-rays are produced in an X-ray tube by scattering electrons through a potential difference or a voltage drop. So we have this vacuum tube with a cathode. Electrons leave the cathode and hit the target next to the anode, and the electrons from the cathode will collide with the metal in the target, the atoms here. This will kick out an electron, leaving a vacancy. An electron from a higher shell will then fall down to occupy that vacancy, and in doing so, a characteristic X-ray will be emitted. This is what a typical X-ray tube output looks like. We've got peaks where these X-rays are emitted from particular shells, K alpha, K beta, and then the L's. There's also a big background, like a humped background here, and that's caused by something called Bremsstrahlung radiation. So when an electron passes near a nucleus, it can be slowed down and deflected, and this loses some kinetic energy, and in order to conserve momentum, an X-ray is emitted in this process. It's called Bremsstrahlung radiation or braking radiation. In the X-ray lab, we'll use electrons to basically produce these X-rays. We then have to monochromate this output just so we're focusing on one fine energy of the X-ray. These are typical lab-based X-ray sources. So for XPS, we tend to use magnesium K-alpha radiation, aluminium K-alpha radiation, or silver L-alpha radiation, and these all have particular photon energies. If we need to use a high photon energy, we can change the X-ray source. If we also consider the X or D instruments, they use a copper source. This has a much higher energy. Aluminium K-alpha emits at about 1486 eV, but it's quite a broad line. We also get a secondary signal from the K beta peak, which is next to it. And so the signals that we get from XPS can be quite messy, and therefore we need to monochromate this X-ray to get a single peak. So nowadays, most X-ray sources have a monochromated system, but in the olden days, if you're using an old one, we might see a non-monochromated system, and the peaks will be a bit broader, and there'll be satellite features here. If this is the output that we get, we then pass the sample through a monochromator, which is a quartz crystal. So we have the X-ray anode, we hit the quartz crystal, and then we hit the sample. We'll see that the energy of the silver X-rays is actually double that of the aluminium X-rays, and therefore In this system, we can actually use the aluminium and the silver together. When we go to the crystal here, we just have to use the second order of diffraction, and then we'll get to that second energy range. So we've got a 2-in-1 essentially. So most of the anodes that we have now, they have silver and aluminium together. So we can use silver, we just have to go to the next level of diffraction there. So when we monochromate the aluminium, the full width half maximum, so that's the width of the peak gets narrower, and that gives us better spatial energy resolution. And it's caused by constructive interference. X-rays, they kind of hit quite a large range of the sample. It's about 1 millimetre in diameter. But when the electrons leave the sample, they pass through an aperture, and the size of this aperture dictates the amount of electrons that we get. Typically, if we don't put a circular aperture in, we use what's called the slot, or the slot aperture, and this is about 700 by 300 microns. Even though we're irradiating a wide area, like in the order of millimeters squared with X-rays, we're only detecting electrons from the middle of 700 to 300 microns, which is good for most samples, but if we do need to get down to some fine features, we can use a smaller aperture. So we can use down to 27 microns, but we just need to bear in mind that at this level of aperture, we are really limiting the electrons, and therefore the counts aren't going to be as high. So we're going to have to do multiple sweeps and look at this for a larger time. Nowadays, most modern XPS systems have a magnetic lens. If we consider the sample and the detector, when the X-ray source hits the sample, photoelectrons come off in all different directions. If we use a magnetic lens at the bottom, this can essentially herd the electrons and get them to hit the detector, so we increase the counts. Without a magnetic lens, you can see a spectrum is quite noisy. When we add the magnetic lens, this increases it by quite a few orders of magnitude, and the signal to noise ratio is much higher. If we consider this spectrum at the bottom, I'm now going to add the top spectrum onto that, and you can see it's very small. We can't even see it, it's just very small on the bottom. So this shows what difference having a magnetic lens makes. So we can use the magnetic lens for most samples, unless we have a very heavy magnetic sample. If we have a magnetic sample, we can't turn the lens on because it might damage the sample, it might damage the holder, so we just need to bear that in mind. A single electron is multiplied to a larger pulse by passing them through channel plates. Copper wires then detect the pulse of electrons, and the timing of the pulse on the wires defines the position, and therefore the energy at each delay line. This then gives us the space on the spectrum. If we do imaging, the spatial position is calculated this way too. When X-rays hit the sample, electrons are produced, and therefore the surface will start to charge positively because we're losing electrons. This is a problem for non-conductive samples because the charge can't be spread around, so we get a charge buildup of positive surface. So if we have an earth metal sample, this is fine because the charge can be compensated by other electrons in the sample. However, if we have a non-conductor or an isolated sample, the charge can't be spread out. This leads to a buildup of charge on the surface, and therefore the electrons that escape start to be pulled back down. This leads to a change in their kinetic energy at the detector, which appears as an apparent increase in the binding energy, and so the peaks shift up the energy scale. And so what we need to do for non-insulated samples is use a charge neutralizer system. So with the charge neutralizer, this will give a stream of a positive charge, and it will stop any problems that we have with the electrons being held tightly. The problem then is that the peaks are all shifted slightly. We need to apply a process of charge correction when we come to analyse the spectrum. What we do is then we align the spectra to a known value reference, so carbon 1s at 285 or 284.7, depending on the type of carbon 1s, is the typical value that we would use. The charge problems that we have, we can try and compensate this by just using a very small amount of sample when we do the prep, so a very thin layer, or by using carbon tape as well, and by applying the charge neutralizer. Why is XPS so surface sensitive? We say it's the top 5 to 10 nanometers of a sample. The X-rays that excite the photoelectrons, these are low energy. Compared to medical X-rays, they're much lower than that. But these X-rays, they can penetrate quite deeply into the sample. However, it's the excited photoelectrons that cause the problem. The excited photoelectrons are relatively slow, and these mostly interact with the material on the way out. If we have electrons that generated deep down in the sample, these will just hit the matter above it, and we will lose them. So we can only actually see the signal from the top 1 or 2 atomic layers. The vast majority of photoelectrons don't get out, and therefore because we're looking at the layers at the top, we're limited to the top 5 to 10 nanometers. And so XPS is a very surface sensitive technique. This is something that we need to bear in mind. The X-rays shan't go right through the sample, but it's the electrons that are only in the top few layers that we detect. And so contamination can then be quite a big problem with XPS. If we consider a metal sample, in the bulk, this will be 99.9% metal, there might be 0.1% contamination. However, at the surface, this is where the contamination will be, and so XPS will show this up in greater detail. So the contamination, it affects most samples. If we have a metal sample, we will pretty much always see contamination, unless this was prepared in a clean room environment, but even then in the chamber, there'll still be a very small degree of contamination that we just can't help. Carbides, oxides, they are a little bit contaminated. Polymers, something like Teflon, nothing really sticks to Teflon. We don't have to worry about contamination so much, but we do need to worry about charging and insulating. So it just depends on the sample. The ideal sample will be something that's compatible with ultra-high vacuum, doesn't degrade over time in X-rays, and is homogeneous, just contains one particular element or one particular compound. So if we just had this, this perfect ideal sample, we could confidently interpret the atomic percentage for this. However, in reality, the surfaces that we get from samples tend to be very different to what we actually get in their bulk. Just using these as a variety of different examples, rust on a wire, this cake is different at the top compared to in the bottom. If we have a layered or a rough sample, what we see at the top will be different. And so with XPS, we need to interpret the atomic percentage that we get with care. So sample preparation is very important. The sample sizes that we use are limited by the entrance port of the machine, the sample holder, and the detector geometry. So these are sample holders from the old instrument. They're quite long and thin. But nowadays, with the new Super instrument, these are typical sample holders that we use.